And hello everyone, welcome back. Welcome back everyone. So in the last video, we were trying to kind of come up with a simple case of a heat transfer between two black surfaces. So let's say you have this curly whirly surfaces for A1 and A2. Okay, so and as we consider that, I want to introduce to you the concept of view factors as we go through the principle of how we calculate heat transfer for between these two surfaces. So let's zoom in, and as with any surface, all right, any surface, what we kind of normally need to do is to consider, well, basically we add up the heat transfer, all right, between subdivided parts of the surface. So let's say we break the surface down and we consider this area here, dA, dA2, and then we consider the heat transfer between dA2 and dA1. All right, so heat transfer between these two. Okay, all right, so and then we repeat by adding, let's say, the heat transfer between this segment and this segment. Okay, and then we add between, we do the same for the third, and so on, so forth, until we have the heat transfer between the whole surface A1 and this small area A2. Once we have that, we repeat this process for this segment, this segment, this segment, and we go etc all the way until this whole area here is calculated, and then we add it up. And basically what you're doing is an integration process, right? Do an integration process, all right, of heat transfer between these two areas until we finish, we finish computing this. So to start out, how do we, let's say, do heat transfer? Before we do the integration, of course, we need to find out how we do heat transfer between two very small surface areas. Okay, so we need to, in general, integrate the heat transfer between the infinitesimally small areas until we get full heat transfer, say between A1 and A2. That's the principle. So step one is to ask, how do we find heat transfer between dA1 and dA2? Okay, so when we come to radiation heat transfer, it's always very important to get a diagram of what you're trying to calculate, because the math can be very confusing. I'll say this many times, the math can be very confusing, so it's always important to have a diagram of what you're actually doing. Okay, so let's say between these two areas, right? These two areas, dA1, dA2, and both are black surfaces. Okay, both are black surfaces. All right, how do we do it? All right, so this baby here, it will be outputting some sort of intensity field, IB, right? And since well, yeah, you'll be outputting some intensity field, right? So let's start from there. Intensity of the black body equals to power divided by, so it's power output per solid angle times the normal area, and that should be about it, I think. Let's take a look at our definitions again. Okay, yeah, radiative energy flow per time, this is power per area normal to the rays per solid angle. So let's say this dA2 for example, or dA1 is outputting this IB lambda, right? And of course, if you want, yes, per spectrum, per wavelength, okay, because this is per wavelength basis. IB lambda means per unit wavelength. So let's say you have a 3 nanometer wavelength, and then you have 1400 nanometers. So you have that kind of black body spectra that you have to consider as well. But for black surfaces, we kind of do away with this. So you have IB equals to integral over all lambdas, B lambda, D lambda. Alright, we want to do away with the wavelength, so that simplifies our analysis. So let's get rid of the wavelength by just integrating. So this is where we get kind of start getting our sigma t to the fourth. Alright, what's the sigma t to the fourth? It is over here. If we consider, you know, the spectral, black body emissive power, which is not intensity, by the way. Okay, but this is where it comes in, and later we will try and do something about that. Find out the relation between the proper relation between, let's say, EB and IB. Okay, so we have this first, and let's say the heat transfer then, or the heat transfer. So you just have to find the Q equals to power, or rather the intensity, times the normal area times solid angle, right? So we'll try and find expressions for each of these. Now what is this normal area then? Alright, so we can zoom in again. Right, I think I want to use a very thin brush, thin brush. So use this. Okay, so this is where the normal of dA2 is, right? And we have an angle theta here, right? And let's call this theta 2, because this is A2. And let's say the normal here is this is the normal here, and this angle then is theta 1. Okay, so what is the normal angle, normal area facing from dA2 to dA1? Okay, so normal angle from dA2 to dA1, so this is the area dA2. The normal angle is dA2 cosine theta 2. Okay, normal angle from, or normal area of dA2 is, so let's just put dA2 cosine theta 2. And likewise, normal area of dA1 is dA1 cosine theta 1. Alright, so so we have the normal areas of both of these. Okay, so let's say we want the heat transfer from 1 to 2. So the normal area of the A1, it will be dA1 cosine theta 1. And what is the solid angle? Solid, as we have found out before, solid angle equals to dA divided by r squared. So this is the normal area divided by the distance between A1 and A2. So let's put that in there. So dA normal over r squared. And if we were to put this in, just substitute the expression in, we will have this. dA to cosine theta 2 over r squared. Okay, so we start to have okay, oh, I should put dq, sorry. This is the infinitesimally small heat transfer. Alright, it's not the whole thing. The whole thing is you kind of have to integrate over both areas. So, I mean, if you want the q from 1 to 2 equals, you need to integrate over a1 and integrate, okay, the a1, and you need to also integrate over a2, the a2, this whole expression in there. Okay, so you need to kind of get rid of this because yeah, you're just integrating over a1 and a2. Alright, this is your generic expression for heat transfer from 1 to 2. Alright, so wherever this r squared is, it will differ every time you kind of shift the areas. What do I mean? Let's say between this one and this one, r squared, this is r, the distance will have a certain value, and if you kind of shift and you compare between these two, your r will differ. So the tricky bit of integrating this is that, you know, cosine theta 1 and theta 2 will kind of differ, and r squared will also differ. Okay, so but this is, at least in theory, how you would do it. And now how do we put a value to this IB? Yep, how do we put a value to this IB? Okay, so let's go to Kindle and you'll see the textbook. You'll see radiative heat flux or radiative intensity. Okay, so let's go back to our little Lambert's law. Okay, and let's find, yeah, okay, so yeah, the next step is of course to find out this IB, and probably we'll do it, yeah, we'll do it in the next video. But now you can see how the geometry kind of starts to play a role, where this how this expression comes about. And yeah, so we need to do some of these area integration. Okay, so I'll see you in the next video. We'll discuss more about this little IB factor, how can we find a suitable expression for this based on EB, based on the temperature, the n squared sigma t to the 4th, and how this Lambert's cosine law kind of comes into play. Alright, so thanks for watching. I'll see you guys next time. Bye bye.